Roman candle with me. Just a Roman candle. You can wear your sandals and I'll pour you just one cup of tea. Then you can go and rest. You haven't seen my best, so just spend an evening with me. Just a lazy evening, then you could be leaving all week and stay and talk it to 3. I think it's magic and I hope you'll agree. So light a Roman candle with me. Just a Roman candle, just a breath of pepper.
Welcome to Cooking for Science. Today we're going to be preparing 3-methyl-2-hexanone. So today we'll be starting off with propanol. And as you can see, propanol has a few hydrogens to it. You have a hydrogen over here and one over here. And this one right here is going to be a really acidic hydrogen. Think of it as a chocolate chip cookie. And over here you have your hydroxyl group. And so this guy is imagine him as a really hungry child. And so he's going to go and gobble up that chocolate chip cookie. And when this happens, these two electrons holding this hydrogen in place move all the way over here to create a double bond. But unfortunately, in order to do that, you got to make room. And so there's a lone pair from the double bond of the carbonyl group that'll go up and make an additional lone pair on the oxygen atom. And so now we have our enolate with our double bond here and our lone pair on our oxygen. And so this is like a really hungry kid who just actually, or like he's on a sugar rush because he just ate that chocolate chip cookie. So now he wants more. And so now he sees his twin brother and they're gonna wrestle. They're gonna wrestle for the chocolate chip cookie. And so as they wrestle, this double bond will attack the carbonyl group of this aldehyde right here, causing it also to make room on the plate and having this lone pair move up onto the oxygen. And this lone pair from this oxygen goes back down to form the carbonyl group again, forming almost our aldol product. But what's missing is our lone pair electron right here. He's a hungry kid, and hungry kids like to eat things. So this hungry kid is going to grab this hydrogen off of this water right here. And as it grabs it, they have the residual lone pair electrons that move over onto the hydroxyl group, forming our aldol product. And then we take our aldol product, put it in the oven, and what comes out is our alpha beta unsaturated ketone. So Riley, do you know how a cookie stays warm?
I don't know, Christian. How does it?
With a cookie sheet.
Anyways, back to the kitchen. So, what we have now is our alpha beta unsaturated aldehyde. And so now we're gonna add a little ethyl acetoacetate. But wait, first, we gotta convert our acetyl acetate into our enolate. Don't boo. It's just the same process as last time, except instead of OH, our hydroxyl group, now we use ethoxide, mainly just to avoid
the basic hydrolysis that would go otherwise.
Yes.
And so, just like every other enolate, we have a hungry child with this double bond. But this hungry child isn't so hungry as to eat an entire meal. So this one is going to eat some pizza, but instead it's just going to eat the crust. It's going to go on the outside. And because they ate the crust, now we have a little bit more room on our plate. And so this double bond moves on to this side of the carbonyl group. But now that our plate's a little bit full on the carbon, this lone pair electron's got to go back onto this oxygen, forming our alkyl substituted product. But now that we have another enolate, this double bond here is hungry for this hydrogen, just like a hungry kid for cookies. And so this double bond is going to grab this hydrogen, causing this lone pair to go onto this oxygen. Now that we have a little bit more room on our carbon group, this double bond from this oxygen is going to go back and form a carbonyl group, completing our Michael reaction.
Hey Christian,
Yeah, really?
why did the banana go to the doctor?
Why?
Because it wasn't peeling well.
So remember how I said that we didn't want to undergo saponification? That's because it wasn't ready. Just like how you want to add the ingredients in the right order, we want to undergo saponification at the right time. So now we're ready. So now we have this hydroxyl group, hydroxyl ion, primed and ready to attack this carbonyl group. And as it does that, this carbon's got to make room. And so now the lone pair from this double bond moves on to the oxygen, forming our tetrahedral intermediate.
And now that we have our tetrahedral intermediate, this oxygen here with the additional lone pair wants to balance itself out and become a little bit more stable. So in doing so, the lone pair moves to form a double bond between it and the carbon there. But in order to do this, it'll bump off the ethoxide group. And then the ethoxide group will react with hydrogens provided by the water to make ethanol. But wait, there's more. The hydroxyl group from before is not done. It'll deprotonate this hydroxyl group added to the carbonyl group to form our carboxylate
anion. And so now this carboxylate anion is destabilized by this negative charge from the lone pair. And so now it wants to be neutral. So now this lone pair from the negative charge grabs onto this hydrogen from the hydronium group, moving the lone pair onto this oxygen, forming our carboxylic acid. Alright kids, so now we're primed and ready to undergo decarboxylation reaction. But watch out, it's a fast reaction, like popcorn popping. So now we have this double bond from this carbonyl group attacking this hydrogen from the carboxylic acid. But with the leftover lone pair electrons, it's going to move over, forming another carbonyl group, getting ready for our CO2 to leave. But before it pops off, this lone pair moves on to this carbon-carbon single bond, forming our enol. And so now this product undergoes a fast keto-enol tautomerization, forming our dione.
And now with our dione, things get a little saucy. An OH group from NaOH will come and take off this acidic hydrogen, form another double bond, and then this lone pair here comes off and forms over there with your oxygen, creating another enolate. And from here, it undergoes intermolecular cyclic formation, creating a cyclic ketone.
And so now we've almost formed our cookies. I can smell them in the oven. And so now we have this lone pair left over from this oxygen, and now it's going to protonate and grab this hydrogen from water. And so now what's left over is this molecule. It's not quite satisfied yet. It's not fully stabilized. It can be a little bit more stable. And so now we're going to place a lot of heat on this molecule to form our conjugated system, forming our 3-methyl-2-hexanone.
Those are some pretty fine looking cookies.
So now we take it out of the oven. Oh, it smells really good, Riley. And that's your 3-methyl-2-hexanone.
I hope you'll agree. So
Thanks
for watching.
home and candle Roman candle, just a perfect apple. Oh.
Making this video, I think, is been an excellent way to wrap up this year in such a fun and creative exercise. And in this video project, I learned that it's one thing to learn organic chemistry, but it's an entirely different thing explaining it and teaching it to those who aren't so familiar with the concepts. And to be able to take such complex reactions and describe the mechanisms and driving forces behind them is just an incredibly difficult skill that I now have the utmost admiration for.
So this was a pretty interesting project. It was fun. It was a challenge just because now I'm understanding while teaching, especially when you ask us to focus on elementary kids as our audience, focus on captivating their attention. So it's one thing just teaching it and explaining the step by step, but then like Riley was saying, to make it simpler and then to be creative in the ways you teach it, so that way they're constantly paying attention is it was a challenge. And I think what helped for me was to try to, for both of us, was to inject some humor into it. And it was fun just in the sense of like making it seem like a TV show. I think that made it help me be a little more comfortable while making the project. And I also realized that there's a lot of team building skills required in it as well, because you have to feed off of the other person while they're teaching, feeding off their energy and trying to make as good of a product as possible.
Hi, Mr. Hilario. We would just like to thank you for basically putting up with us all year and really teaching us the material we need to know.
Yeah, thank you so much for all the hard work you put into teaching, and wish us luck in biochemistry for next year.
Yeah, definitely.